Good morning and thanks for joining us today for this technology webinar. My name is Chris Judge and I'm the machining specialist here at IMR. For those not familiar with the IMR, we're a technology research centre who work very closely with industry, supporting their needs by helping implement new and emerging technologies. We are now developing out the machining function and have a machining lab based in Mullingar with equipment to help us work with industry around these technologies. In today's webinar, we will be giving an overview of 5-axis milling strategy called Barrell Milling or tangential milling. Some companies are very familiar with this strategy and are currently using. We would like to, most would relate it solely to the aerospace machining, and today we want to demonstrate the possibilities for use in 5-axis machines and in sectors from medical device to general component manufacturing. We will demonstrate the potential time savings of using such technology and where to implement. I'm delighted to demonstrate this technology, which uses different types of tool paths and tooling. We've invited two IMR partners to discuss this with us. Andy Moore from Hard Metal, representing Moogie Franklin and Nishgar, and Simon Docker of Hypermill with us this morning. Both of these guys are experts in their field, and the Moogie Franklin and Hypermill companies were heavily involved in developing this technology. So Andy, over to you, please.
Thank you very much, Chris. Good morning, everybody. As Chris indicated there, I'm Andy Moore, Technical Manager from Hard Metal, and today I'm going to introduce you to two companies, both Iskar and Moogie Franken, who have been involved heavily in developing the 5-axis milling strategies using the concept of barrel milling. Moogie Franken has a full range of standard milling cutters, but today I'm going to be talking about what they would call as circle segmented end mills. Circle segmented end mills have the possibility to reduce cycle times by up to 90%. How we can do that is because when we look at today's technology for producing thin-walled surfaces, high walls, concave or convex surfaces, we have to scan using a traditional ball nose end mill. And typically, if we looked at a 5mm radius or a 10mm diameter ball-nosed end mill, we would have to take down steps of 0.2 of a millimetre in the AP, in the step down, in order to achieve a high surface quality. So we're trying to achieve a small cusp height between the two steps. And this is where we have to take small axial depths of cut, and this can be very time consuming in order to achieve a high surface finish. Back in 2012, Moogie Franken and OpenMind got together and tried to think how they could solve this problem of reducing the cycle time dramatically. And on a sketch of paper, they basically came up with the concept of circle segmented tools. So how does the system work? Firstly, it was a challenge for both OpenMind and Franken together to define a geometry that would work against the workpiece, and for Franken to produce a tool geometry with very high manufacturing tolerances. So it was very much a partnership between the two companies to try and develop this technology. So again, just to reiterate, when we look on the left-hand side, we see the traditional method of producing a thin wall, or a concave or a convex surface with small step downs, small cusp heights in order to improve the surface quality. Whereas you look now onto the right-hand side, you'll see a very different shaped tool where we have a large radius, R2, of 75mm. This then enables us to take a much larger step down in the AP direction and create very small cusp heights between each step down, creating a very high surface finish. So this is where the concept was born. If we put that into practice, if we look at a typical component here that we'd have to feature and produce this concave surface using a ball nose milling cutter, in order to achieve something with a 75mm radius, we'd need a ball nose end mill of 150mm in diameter, which is totally impractical. So what we do, we take a tool, part section of a tool, and we create the radius of 75mm on a segment, hence the term circle segmented tools. And now we can produce that large step down, whereas conventionally we would have been using small step downs. And this is how we reduce the cycle time dramatically. Now, within the Franken range, there are 4 types of circle segmented tools. The terminology barrel comes from this type of tool where it is literally the shape of a barrel. But here we have restrictions in terms of the corner radius at the bottom and being able to get into tight corners. So here we have two options, either the oval form or the taper form. Both function exactly the same, but have greater radiuses depending on the two. But also both have a small conical radius at the end of the tool, which enables us to get right into the bottom fillet radius between the perpendicular wall and the horizontal wall. So to summarise the range, it was developed, as I say, back in 2012. The range expanded in 2013 to include the two versions of the traditional taper and the taper tool. And then in 2015 and 2013, they developed the lens type cutter. The lens cutter would be predominantly used for scanning flat surfaces or at the bottom of pockets. In 2017, a further expansion included basically tools for machining turbine blades and the like. So these were specially developed with special geometries and through coolant capability. In 2019, they extended the range again with much multi-flute type tools and even an indexable system. In 2020, the plan is to introduce micro circle segmented tools or barrel tools, and that will be phased in over the course of the year. They were to be introduced in A and B, but unfortunately, as we all know, all of those sort of shows have been cancelled. So yeah, just to summarise, multi-flute options up to 6 teeth for both the taper form. These are used mainly on hard materials where we're taking small radial depths of cut. The new innovation of indexable systems gives us the flexibility to reach deep cavities. As a supplier of both Imugi Franken and Harmetal being a supplier of also ISCAR, ISCAR has developed its range of circle segmented or barrel mill type tools, which gives us the possibility to work within the medical industry because of our experience with machining the likes of cobalt, chromes and titaniums. What ISCAR have done is quite interesting in the fact that they've introduced the multi-master version, which gives us the possibility to use indexable heads in both the lens type, the tapered form type, as well as having the traditional solid carbide end mills. And as I say, given our experience within the medical industry, we are actively looking at developing tools specifically for producing the likes of the femoral knee. I'm just going to show you just a couple of videos before I move over to Simon. And this is usually to show you the tools in action. This is an example of an aerospace type component, sorry, a medical component made from aluminium using two types of the form cutters, the oval form and the taper form. And I'll just run you the video now. Just moving on now to the next video, the rest of it was basically just face machining. So this is another example. This is using the tapered form tool, again, an aluminium component, mechanical engineering. It's just showing the tool again in a different slightly application area. Okay, what I will just add before I hand over to Simon is that it's key to use the CAM package is vital in the success of using circle segmented tools or barrel mill type tools. So I'll now hand you over to Simon Docker from OpenMind.
Okay, well, thank you, Andy, and also thank you to the IMAR for inviting me to join this webinar this morning. Much appreciated. So I'd like to focus on an aerospace structural part in the next few slides and some of the challenges that we experience today. We're seeing that the corner radius in pockets have been reduced to make parts lighter, and I see some very deep pockets. And when you combine a small radius in the corner with a deep pocket, this creates a machining challenge. Parts are becoming more complex, and certainly during the current situation, prices are being driven down. So really, how can we be more efficient, more productive, and reduce costs? Now, as Andy has already touched on, how we can achieve faster cycle times using a combination of conical barrel tools or circle segment tools, as they may be called. But let's look at how this is possible. So what is the concept behind the design of a conical barrel tool? Well, as you can see, there is not only a long radius along the flute length of the tool is also tapered and ball nose. Now I'm referring to this tool here. So this is where the tool is very effective, and as a taper forces the tool to tilt, avoiding the collision between the part and the tool holder, and the ball nose allows us to use the same tool to finish areas such as small radiuses in the corners of deep pockets that I mentioned previously. So because you're tilting the tool away from the part, this allows you to keep the tool length to a minimum, and therefore tools are more rigid and less likely to produce tool chatter. So the potential gains can only be achieved if the CAM system has the necessary cycles, as Andy has just mentioned. So to utilize these types of tools within Hypermill, there are dedicated cycles that have been developed especially for use with conical barrel tools, and I'll explain what these are. So the first one is tangent plane machining for planar surfaces, and it's extremely useful when machining deep pockets and hard to reach areas using conical barrel tools. Now, typically to machine a deep pocket such as this one here, a ball nose tool would have to be used with the head tilted over to avoid the collision with the tool holder, but you would only be stepping down probably, what, 0.2 of a millimeter, for instance, so the machining times will be obviously much greater. However, with the combination of conical barrel tools and Hypermill tangent plane machine, you could be stepping down up to 6 millimeters, yet really still achieving a superior surface finish. Here's another example of a lens style conical barrel tool where the barrel radius is on the bottom of the tool, and these tools are useful when machining the bottom surface of very deep pockets. A conventional end mill couldn't be used in this instance because due to the sheer depth of the pocket, that would be impossible because the tool will be too long. So again, the tangent plane machining cycle will be used for this face also. So let's compare the machining of a planar surface using a ball nose tool against a conical barrel tool. Now, as you can see, if I run the video, as you can see, the step down is much greater, so the cycle time will be much, much quicker. Now, this all seems so simple and obvious, doesn't it? But what is the technology behind the max machining cycles that makes them so special? Now, as you can see, as the head is traveling along the face, as the tool is traveling along the face, the head is being tilted simultaneously away from the surface, and this avoids the collision between the holder and the part, and also reduces the excess material left in the corners. Now, if I can stop the video at this point and just go back one moment, just slightly. So the very fact that we're stepping down at 6 millimeters, this will leave a wedge of material in the corners. But within the same tangent machining cycle, and you can see the wedges here, within the same tangent machining cycle, there is an option to clean up the corners using a rest material style approach using the ball of the tool. And I'll let that continue, and you can see here. So within the same cycle, using exactly the same tool, almost 2 cycles combined into one, using both elements of the tool. So we conclude that this is a multifunctional tool and CAM cycle to utilize the whole tool and reduce the need for additional tooling to be used. And obviously the time comparison says for itself, it's much, much quicker. Okay, so here's the same cycle and tooling, but we're actually machining an aerospace structural part. Now I'm going to stop the video at this point once again, because you may notice that the head is fixed at the same angle when machining this area here, as this edge of the pocket is open-ended. So Hypermill is only moving the head when necessary to avoid unnecessary axis movements. And you'll see that if I play it. So it's fixing the head, no need to move the head. And now only when the pocket is contained does it then switch to a simultaneous 5-axis motion. And this is a completely automatic process. So here you can see it's fixed the head, no need for excessive movement at this stage, only when it needs to. When it's within a contained pocket, now does it switch to the simultaneous movement. Whoops, it's gone back. Okay, there we go. Once again, it's fixed head position within a contained pocket. It now switches to a simultaneous movement. Now, this is a completely automatic process, as is mentioned, and it's almost one of the most simplest cycles of Hypermill. It's a completely automatic cycle. It's probably one of the easiest ones within Hypermill, in fact, to program, because it's simply a process of selecting the surface and hitting go. I'll let it continue. And this is pausing it once more, this is where it flicks to the ball of the tool to pick out these wedges left, that the body of the tool left in the corners. And these are automatically removed in as I mentioned, almost like a bounding or a rest material process. One tool to do the whole of that pocket. Okay. Okay, so now let's move over and focus on where these tools and CAM cycles can be used to machine medical parts. Now, in this instance, we'll be looking at a femoral knee surface. Again, we can achieve a massive cycle time reduction, reduce tooling costs, and we really can increase the accuracy of the machining also. So the previous cycles that we used was called tangent plane machining for planar surfaces, but now we're actually machining a 3D face, and this is where we use tangent machining. And these can be convex, concave, doubly curved surfaces, and we have a cycle called simply, as I mentioned, tangent machining for 3D faces. Now, similar to the tangent plane cycle, in collision areas where the tool is automatically tilting upwards away from the contact point, while still remaining in the contact with the part to reduce witness marks. Obviously, the more we retract, the more we re-enter the part, this will leave unwanted dwell marks, for example. So, if we look at this area of the part, that was machined conventionally using a ball nose tool, and then again with Hypermill tangent machining using a conical barrel tool. When we weigh up the cost of the tooling, the machine rate per hour against the total machining cost, although the cost of the tooling, the barrel tool, is higher, the total saving is actually 83%. So I think you'll find that's quite staggering. So it's plain to see that the combination of conical barrel tools and Hypermill max machining cycle is much quicker than conventional methods of machining. But let's see how we can put this into practice to program this femoral surface.
We're not limited to what type of surface we can machine. Okay, this is a complete, organic shape, as is many cases in the medical industry. In here, I've actually included spindle geometry. It's a nice part of our software, is that you can actually calculate and check against the spindle from calculation as well. You don't have to wait until simulation. So this is tangent machining, and this is also a cycle that has the capability for automatic surface extension. And it's quite nice for these areas, okay? Certainly when you're doing freeform. So again, I've just picked the surface that I want to machine. And we can get a real nice result going down here. So what's nice about this tangent machining is with certain controls, you get feedback on how you want the tool to machine this surface, whether you want to go up, down it, which side of the surface you want to machine. You get nice feedback as to what it's going to produce. Now you can see this is a lovely clean toolpath actually it's created. We'll just close the cycle off a second. Okay, so we can see it tracking the surface. Obviously the surface extension did fill in the gap in a little bit, but the less retracts you have to do off the part, less repositions, the better. So that's where also it helps. You can see, if I just turn the model to the side a little bit, the contact at the moment I actually have set towards the tip of the tool. Okay, so this is something that we can actually manage inside Hypermill. Is how much of that edge or what contact point on the circle segment are we using? Now, when you're doing certainly hard materials, you can probably get quite heavy wear using the same point. You get notch wear and all the rest of it. What we have the capability to do is control the contact parameter, and it's dynamic. So I could start at 0.5, which is halfway up the barrel, and I could end on 0. So I'm utilizing the full edge of that tool. Or I could start at 1 and then utilize it. Okay, so we should see now first cut. You see the contact point is now halfway up the barrel for the cuts, and it will adapt and slowly change the contact point as the further it gets down the surface. So if I was to skip maybe down towards the end. Just rewind a little bit. So now no longer utilizing halfway up the tool, it's utilizing the tip. So that also, this control allows you to sort of eliminate the heavy first cut that you often get, and also the rest material that will be left at the bottom of the surface. Okay, by tilting the tool forward and utilizing closer to the tip, you get closer to the form and you don't leave the wedge of material.
Okay, so yeah, I mean, to have that level of control where you can vary the contact point, and gradually balance the wear on that tool is really quite a innovative and unique feature, I believe. So keeping tool wear to an absolute minimum and having full complete control over the contact point of that tool. Now, one of the common questions, is as this is a completely organic 3D surface or shape, although many tooling providers provide off-the-shelf conical barrel tools, it's quite common that we need to use custom tools. And companies such as Hard Metal can provide both standard and custom tools. But how do we know what the geometry of the custom tool will need to be? So here goes.
Okay, so the most common case of having or choosing your barrel radius size comes down to the geometry that you're machining. Now, when you're machining flat planes, okay, you go as large as possible in here to maximize your step down, okay? But with freeform geometry, it all depends on, first of all, surface finish requirements, whether these surfaces are being worked afterwards. I know in this instance, these surfaces are actually finished, so they're only after sort of a finishing operation that gets you to within sort of 0.1, 0.2 of the surface as quick as possible. And that's where barrel tools have come in on this surface. To select my barrel tool size, I actually look at some of our analysis tools, and we've got a tool here called Face Spherical. So for this surface, Face Spherical places a ball or radius on the surface, and by increasing or decreasing the sphere size, you can start to see failure. So it's quite often common to get a barrel mill with 1,000 radius. So I'll type in sphere size on radius mode 1,000, and I can see tracking over the surface instantly in red. I'm going to struggle to get the tool tangentially in there for a nice roll around. So that to me is an indicator, right, I need to start decreasing my barrel size. I'm not properly going to hit all of the surfaces. Now, when you're looking at tangent machining, okay, and you're using drive surfaces, it's collision checking against the surface. So as long as it's rolling over, you know it's not going to gouge into the model. Okay. You can see around the 40 mark on these areas. So this is a good tool to get a rough size.
Great. So another common question is, how do I know what step over to use to achieve the maximum cusp height that would be allowed? Obviously, we can see that we can take much larger step overs when compared with bullnose tools, but we still want to maintain that cusp height. So here we go.
One of the nice tools that we can use here is shape to shape distance. So shape to shape distance, I have my surface as one surface, shape A and shape B. I can use my stock model left over from the cycle, and you know, with a little bit of tolerancing factors, let me get to sort of 10 micron tolerances, I can now get a really nice color map going of this area and feedback at cursor point as to my scallop height. Okay, so I think with this part, I've got 50 micron maximum scallop left over from the barrel machining, which is absolutely, you know, enough for this surface with the work that's happening afterwards. But that figure is depending now. Okay, can I increase my step down by another 2 mil? Yeah, you just check in against what your known parameters are and adjusting the tool size and barrel radius to suit to get the maximum quickest result. So yeah, a couple of tools there: Face Spherical, shape distance for checking the stock model afterwards.
Okay, super. So, so the IMR really very kindly cut this part on their facility on their Hermony C42, so that you can see the tool movement and see the surface finish you can achieve. I'll run that video, and I really do hope that you can agree that the results are pretty good. The obviously Hypermill is restricting the tool movement. We don't want that tool flying all over the place. It's a great surface finish, well within the tolerance that we need. And I must stress, however, that this is only a concept part, so it was machined in aluminium. So it was just to really give you an idea of how Hypermill is controlling the tool across that femoral surface.
Just to add to that, if you don't mind, Simon, just to point out that the tool that was actually used was a 10mm ISCAR taper barrel tool.
Thanks, Andy. Okay, yeah, I'll flick to the next slide now. Okay, last but not least, another real high level of growth within the Hypermill user base is the use of Hypermill automation. Now, it's designed to reduce programming times, especially for parts of a similar nature or for parts, families of parts, as they may be called. Now, Hypermill automation uses methods defined by the user and applies the same methods on the next part. So especially for medical parts where the shapes are similar but only the sizes are different, the programming times could be reduced to, well, almost zero in some cases. And really the same applies to aerospace parts also. So I just wanted to drop that in, that Hypermill automation is available, and it's certainly becoming extremely popular, especially during these really difficult times. So that really concludes my presentation. And once again, I'd really like to thank the IMR for inviting us to present today. I hope that you found the presentation interesting. So at this point, I'll pass you back to Chris.
Hey guys, thanks very much. That was very interesting and gives a really good overview. I hope that helped to clear up a few things around the topic of barrel milling, and I would like to thank everyone for attending today. I'd particularly like to thank Andy and Simon from our technology partners Hypermill and Hard Metal for supporting this today, and would like to be doing more of these types of technology days in the future, either online or ideally at our facility in Mullingar, where we can do live demonstrations on the back of this. And if you have any questions about anything that you've seen here today, please reach out to one of us. Or if you have any questions about the IMR or think we might be able to support in some way, or would like to see some other topics covered in these technology days, please let us know. Again, thanks for your time, and we hope to see you soon. Thank you.